1957, the Russian space program launched Sputnik, the world's first electronic satellite. Everyone knows that it circled the Earth, sending back the familiar beep beep that anyone could hear on their wireless set at home. But what is not generally known is that simple signal contained information about Sputnik itself. The length of one beep indicated its temperature, and the length of another, leaving a gap in the first, indicated its internal pressure. This simple form of telemetry from a device which would otherwise be lost to the heavens was the inspiration for another, rather less ambitious project. Like Sputnik, it too would be sent on a journey from which it would probably never return. A journey which could take it to faraway places, over hills and mountains and seas. A journey which it would take alone. Alone, but not forgotten. Like Sputnik, it too would send back signals containing information about itself. Signals that anyone could hear on their wireless set at home. Signals which could also be used to find it. Signals from the Wireless Wanderer. The Wireless Wanderer is a nomad. It goes on its own wherever the wind takes it. But it's my nomad, and I'd like to know how it's getting on. Okay, this is all the electronics it has on board. It's powered by two 6-volt batteries. This lot is the arc transmitter. The transformer is an ignition coil from a car, so the HD is about 20 kV. This is all the electronics that generate the signals for the transmitter. On the bottom here is a switch which detects if it's landed. This is a tilt switch. The idea of this is that if it gets caught in a tree or something, we can detect if it's not hanging vertically. The Wireless Wanderer uses a small array of detectors to build up a picture of its overall condition. Electronics organise the detectors into signals for the transmitter to broadcast. To keep down time spent on the airwaves, as well as power consumption, an onboard clock regulates the use of the transmitter, the most power-hungry component. Because the transmitter is so close by, the clock must be protected from it. Aluminium foil serves as a Faraday cage. One contender for inclusion in the project was this, the lead line altimeter. The altimeter is a fairly simple instrument for finding our height above the ground by timing how long it takes a weight to fall. When I give it a signal, it drops its line, and while it's dropping, it generates an output signal. When it finds the ground, it detects that it stopped dropping and winds it back up again. But for all its ingenuity, the lead-line altimeter presents one or two practical problems, not the least of which is the amount of power needed to wind it back up. The length of line we'd need, I think we expect to be a few hundred feet up in the air. Then there's the risk of getting the line caught up in trees and things. I'm not sure we can carry enough. String or even thread are rather bulky, and we'd be going around and knocking on people's roofs and heads, and that wouldn't be good. So the altimeter will not be amongst the Wanderer's instruments, but as Simon explains, there is an alternative. Triangulation. You're sat at home, here in Biggleswade, at just before the hour. When the signal comes near enough on the hour, you turn your radio until the signal is strongest. If all's well, you've got 30 seconds. Now you can't be very precise, but let's say you narrow it down to this sort of area, this sort of angle. Now it could also be somewhere in that area. What you then do is you go out to somewhere like Broome or Sutton with your little radio. And you look for the signal again, and let's say you find it somewhere in here. Now, it could also be somewhere in here, but you already know it's somewhere in this area here. What you then do is go and find it. Go and find it, get close to it, but not directly underneath it. Measure your angle, measure the angle, theta, and estimate your distance, and then use h equals s sine theta to find the height. That's the altitude. The Wanderer's transmitter broadcasts on a frequency about 1 MHz. Ideally, an aerial 246 feet long would be used. This is more than a quarter of the height of a major local landmark, the mast at the Sandy Heath transmitting station. 246 feet is the optimum length for the Wanderer's transmitter to broadcast efficiently, but if it emerges that an aerial that long is simply too heavy, then a shorter one could be used, one exactly half the length. Of course, we'd like to use a quarter wavelength aerial, but it's quite possible that an aerial that long wouldn't be able to support itself, and one that could would be too heavy. So we might have to consider a shorter aerial, an eighth wavelength, 123 feet. With work on the electronics complete, comes the work of getting the equipment airborne, in its own way as equally challenging as getting it on the airwaves. But with no fixed launch date, there is no hurry. It will come when it comes. The WirelessWanderer is a nomad. It goes on its own wherever the wind takes it.